saying before, hopefully you were able to factor this, but let's say you tried and you were like, I can't think of what it could be. First of all, I hope you know that it would have to be 5x and x, because that's the only way to get 5x squared. But let's say, for whatever reason, you're having trouble figuring out two numbers to multiply by 6 and everything worked out. So you've given up and you go to your quadratic formula, which says x is equal to negative b plus or minus b squared, which would be 169, minus 4 times a, which is 5, and c, which is negative 6, all over 2 times a. So we do some math here. We get 289 in here. You go to your calculator, and 289 happens to nicely be the square root of 17. And so you get negative 13 plus or minus 17 over 10. And that will be two different answers. If you do the plus, negative 13 plus 7, you get x is equal to 4 over 10, which is 2/5. And if you do the minus, negative 13 minus 17 is negative 30. Negative 30 divided by 10 is negative 3. So that you know that your answers are 2/5 and negative 3. Well, if x is negative 3, does it make sense here that you'd have to have an x plus 3? And as soon as you have a plus 3 there, in order to get the minus 6, this would have to be a minus 2. And sure enough, that gives you the x equals 2/5. So you can use your quadratic formula to figure out your factoring. If the question said solve by factoring and you're like totally stuck, you could use a quadratic formula on a scrap piece of paper. Then figure it out. Then write out the factoring. And like probably, because you wouldn't want me to know that you cheated and did a different method, you should probably then rip up that small piece of paper and eat it, swallow it, so that I don't see that you weren't able to factor directly. But then you'd be fine. No problems whatsoever. A rectangular construction site is to be enclosed with fencing. The length is 15 meters longer than the width. Are you okay with this way of showing the dimensions?
Yes. Oh, no, it does say exactly 15 meters longer.
Yeah. So the area is going to be length times width. That's the area. And we're told that the dimensions of at least 700 has to be enclosed. So this is an inequality that this area, does it make sense, has to be bigger than or equal to 700. 15, thank you. It's there, just didn't see the one. It has to be bigger than or equal to 700. This is now a quadratic inequality. Now, you could solve the equals part, right? I could multiply this out and make it equal to 700. Make one side equal to 0. What's not fun about factoring this one? The 700, right? Because of big numbers. So you might want to go to the quadratic formula because you don't like the big numbers. Anybody know two things that multiply to 700?
1 and 700.
107. Is that going to give us 15?
No.
Right? So did you know that you can find other ones by like stealing numbers from one and moving it to the other? Like you could take 10 out of this one and make it 10 and 70. You could do that. But still doesn't give me 15 of a difference. What do you see? 20 and 35. Right? Take a 2 out of this one, move it there, cut that one in half, 35. And sure enough, if you make it plus 35 and minus 20, then you have two possibilities for x. So x could be minus 35. Have you ever built a fence with a width of minus 35 meters? Somebody like, no, never built a fence before. Well, the minus 35 doesn't make sense because it's a negative number. So then the 20 is the only thing that makes sense. Now that's when it's equal to 700. What did we want? We wanted at least 700. Does it make sense that you would have to make the width has to be greater than or equal? That would make sure that you have at least 700. How many answers to this question are possible? Millions, infinite, right? Because you could say, I'm going to make it 100 and 115. You have at least 700, perfect, right? But if the question was, someone says, we want you to build this, it has to be at least 700, give us a quote, well then you would want to, if I'm giving someone a quote, I'm going to make it as small as, like, just barely meet their expectations. And say, I did exactly what you asked. You got exactly 700 for my quote. And they're like, we wanted more. Well, you said at least 700. I did that. So these are inequalities. Sometimes you have a situation where you want something exact. So this you have at the top of your next page. Quadratic inequalities in one variable. By one variable, the only variable that's in each of these is the x. There's my one variable. The a, the b, and the c are numbers. Later we're going to do quadratic inequalities with two variables. And so we have to find out how to solve a quadratic inequality. And what I'm going to get you to do is on the side of the page on 341, we're going to write down a little bit of notes. How to solve a quadratic inequality. Just like solving quadratic equations, you make one side equal to 0. And then we're going to solve it like normal. You're going to solve it, and you're going to change your inequality if it's less than, greater than. You're just going to say, I'm going to find out when it's equal to 0. Because those are going to be critical points from changing when something is true to when something is false. So we call those changing points critical points. But this is just basically, that's chapter 3 that we've already done. You know how to solve quadratic equations. You could do it by factoring. You could use the completing the square method. You could use your quadratic formula. However you need to solve it, you solve it. And then we're going to use something called test points or the graph find out where the inequality, I guess I should write inequality. Find out where the inequality is true, and then finally, once you know where it's true, you're going to write out the solution. So and another notation thing, if you have these signs, we'll write this down and you'll see when you look back, you'll know what we're talking about later. But for now, you don't quite know what we're talking about with open circles and closed circles yet. Write it down and we'll see in an explanation shortly. So we're going to follow through on the examples that they have for us on page 341. You can just watch as we're going. Is everybody done writing this down? Yes? Not quite? Almost? So here you've got a quadratic function, y equals x squared minus 2x minus 3. So first of all, if we made it equal to 0, like they've done right here, that would find this point and this point. Where it's equal to 0, you make y equal to 0, those are your x-intercepts. Next, the question is, what happens if we replace the equal sign with a greater than sign? On the graph, they're asking, when are the y values bigger than 0? Because this was my graph of y equals, and we found out where y was equal to 0. Those were our x-intercepts. And now, we're basically asking, since this part in the graph is your y, we're basically asking, what points on your graph are your y-coordinates bigger than 0? Well, does that make sense that from this point on and this point on is where your y values are bigger than 0? And that happens when your x values go this way and this way. If I need my y values to be bigger than 0, that happens when my x values go this way and this way. So how do we solve an equation like x squared minus 2x minus 3 is greater than 0? Well, this is where we wrote our steps out. Okay? First, we make one side equal to 0 and solve as if it was equal to 0. So this is basically step 1 here. Right? This was step 1, and you found out that it's equal to 0 at negative 1 and 3. Then step 2 says, use test points, oh, that's step 3. Once we've solved it, use test points over the graph to find out where the inequality is true. So in the first step here, they used the graph. They said, this is where my graph's y values are bigger, so then my solution is when x is less than negative 1 and when x is bigger than 3. And they wrote the solution out right here. X is less than negative 1, x is bigger than 3. We could also do this with test points. So this is the second example in between. And they said, if it was less than 0, you would still have these points, but now we're looking for where the y values are negative, so it would be the section in between. One of the strategies we're going to use is we're going to find out where it's equal to 0. And that was at -1 and 3. And this is where the open circle and closed circle idea comes in. Since the original equation here just has a less than sign, we use open circles to say that those values aren't included, because those are where they're equal to 0. If the equal sign was included, we'd fill in those circles and close them to say they're part of the solution as well. So open circles means that that's not part of the solution. And what I mean by test values is I would get you to write your number. I'd get you to mark -1 and 3 and put an open circle at -1 and an open circle at 3. And can you tell me a number between -1 and 3? 2, 0, there's lots of choices, right? Mental math-wise, choosing 0 is really nice. Look at your equation right here. What happens if you plug in 0? You would get 0, -0, -3. Would you agree that the left-hand side, when I plug in 0, is -3? Is -3 less than 0? True. And I'll get you to put a T in there to say that that section is true. That's using a test point. What is a number bigger than 3? 4, 5, doesn't matter. Put in 4. Something you can do that's not too hard. 4 squared, 16. Minus 2 times 4, 8. 16 minus 8 is 8. Minus 3 is 5. Is 5 less than 0? False. A test point tells us that section is false. The graph. Can you see the graph is at 4? On the graph, I have that point up there. The y value is not less than 0. The graph also tells us it's false. What is the graph going to tell us for something less than -1? The graph is going to tell us it's false in that section. If I plugged in -2, this would be 4. -2 times -2 plus 4, 8. 8 minus 3 is 5 again. Not less than 0. So what we're going to do is we're going to use our critical numbers to draw a number line for the x-axis and say where it's equal to 0. Then either use the graph or test points to see where it's true and where it's false. So here's our first example. Step 1. I'll draw the parabola, or I'll move it over and make one side equal to 0. And then I'm going to solve for the critical points. The critical points are when this is equal to 0. Make your decision which method you'd like to solve. Do you want to use completing the square? Do you want to use quadratic formula? Do you want to factor? Okay. As you get better at it, factoring will always be the fastest if you're good at it. How do you get good at it? You try. So I would always try factoring first. The nice thing about trying factoring is if it's not working for you, you always have the quadratic formula to go back on. I don't think I'd like to use completing the square here because it has lots of fractions. Seems a little annoying, so I'm just going to be like, yeah, I'm going to avoid that right now. Does it factor? Well, if it did, this would have to be 3x and x, and this would have to be 1 and 1. It's not really much decisions to make yet. Just have to figure out plus and minus signs. Can I get 2 with my outside and inside? Yes. Outside would have to be plus to give me plus 3, minus 1. Perfect. So my critical points are at -1 and at 1/3. So we draw our number line. Does it matter where the numbers go? The -1 has to be on the left. and the 1/3 on the right. Your scale doesn't matter. Will I use open circles or closed circles in this one? There's just a less than sign. So I'll use open circles to put those in. What's my solution? Well, now I can either use my graph or my test points. What do I want? I want it to be less than 0. Plug in 0. 0 is the easiest one to do. As a test point, 0 plus 0 minus 1. Is minus 1 less than 0? Yes, this section is true. Okay? Now, in parabolas, if the middle section is true, almost always the outside sections are going to be false. If the middle section is false, the outside sections are going to be true. That happens with parabolas. When you get into calculus in grade 12, we do something similar to this again, but it's not always going to work out perfectly that they alternate. Okay? So, I'm going to do a test point bigger than 1/3. I'm going to pick 1. If I plug in 1, this would be 3. Plus 2 is 5. Minus 1 is 4. Is 4 less than 0? False. I'm going to find out the other one using the graph. Okay? And when I graph this, I'm going to use factored form. If you were graphing this, does it make sense that the only thing you figured out are the y-intercepts? You figured out -1 and 1/3. If this is my parabola, does it open up or does it open down? It opens up. So here is my parabola, like this. What am I trying to find out? I'm trying to find out where my parabola, which is equal to y, is less than 0. Can you see that in only this section here? That's why the middle section was true. It tells us that this section on this side has to be false as well. So the graph, right? When you make this number line to show your work, I don't know if you've used test points. You don't have to show your test points to verify the true, false, and true, or you used your graph. I know lots of people find it and then quickly use the graph to do the true, false, and true. So this graph that I drew is this graph. Y equals 3x squared plus 2x minus 1. The inequality we're trying to find is where what I've circled here, that's my graph. This is my graph, is less than 0. My graph is my y values. Because all of this is equal to my y values. So I'm really saying, where are my y values less than 0? That's everything below the x-axis. My y values are less than 0 when it's below the x-axis. My y values are bigger than 0 when it's above the y-axis. So looking at the graph, I'm like, oh, it's only the yellow part where that's the true part. These parts are false. So it can be a very quick way, because all you have to know is whether it's opening up or opening down to find out where it's true or where it's false. Does that make sense? So our solution, you can write your solution in a couple of different ways, right? They ask for the solution on the number line, so then on the number line, open circles, connect those two dots, that's the section that's true. Writing out our solution, you can either write it out like this, which is called set notation, or you can write it out in interval notation. In set notation, when we have an open circle, there's no equal signs. In interval notation, when we have an open circle, we use round brackets. If there was an equal sign, in interval notation, we use square brackets. And in set notation, the equal sign would be there as well. Questions for practice. Try 4, 5, and 6.